Well, so I'd like to tell you a short story which is involving two fields where I have been working in. One is the theory of differential equations. The other one is number theory. And then there is a third field, which is Fourier analysis, which provides tools to solve problems in both of these fields. So over the recent times, and especially in the last few years, there has been reasonable progress on the level of the Fourier analysis, which is very encouraging to anticipate feedbacks, say, in the area of number theory and in the theory of differential equations, the way it also happened in the past. So, since we are talking about the past, historically, we should go back perhaps to Jean-Baptiste Joseph Fourier, in particular, who was a personality with many facets. He was a mathematician, a physicist, historian, administrator, and on the physical side, he is very well known for a treatment, in fact, the first treatment of propagation of heat in solid bodies, the derivation of this equation from basic physical principles like Newton's laws, and on the mathematical side, the use of the Fourier transform to solve that equation. So since we are talking about Fourier analysis, what Fourier realized, his basic discovery, is that arbitrary functions can be actually represented in a much simpler way with a superposition of elementary waves, such as sine, cosine, x, sine 2x, etc. For instance, as you may have seen in the video yesterday, if you take a complex musical sound which is produced by a vibrating guitar string, it can be synthesized this way and can be synthesized as a Fourier series, and it will tell us what are the frequency components. So the basic mathematical problem in Fourier analysis is to understand how these frequencies interact, and these interactions can be possibly higher dimensional. So it is an active research area leading to important advances in both of these theories of differential equations and in number theory. As I said, this happened historically probably more than what Fourier ever anticipated. And our new insights, they bode well for further progress in the near future. So since we are bringing into play two different fields there, let me just say, just very quickly, with some concrete examples, how problems of number theory through Diophantine equations enter issues of frequency interactions. So what you see there are two systems of equations. So the first system there are two equations in 6 variables. The second system has 8, there are 2 equations now in 8 variables. This first system of equations is closely related to the theory of the Schrödinger equation, while the second system relates to another physically, mathematically important equation, which is the Korteweg-de Vries equation, and for instance modeling the propagation of waves in shallow channels. So it turns out that this first problem is actually a rather elementary number theoretic question, while the second problem with the 8 variables and where the square is replaced by a cube turns out to be much harder and is still unsolved. So we are entering here another area, which is that of Diophantine equations, meaning understanding integral solutions to algebraic equations. And this also is a field with a long history. And some prominent names there are, for instance, Lagrange, who lived slightly earlier than Fourier, and also Waring. So Lagrange, as I said, Lagrange was a French-Italian prominent mathematician, also well known for his work in celestial mechanics. For instance, he discovered the Lagrange equilibrium points 100 years before they observed the Trojan asteroids, which is a little bit like the story of the gravitational waves predicted by Einstein's theory to some extent. But anyway, as a mathematician, he had important contributions to number theory, and perhaps one of his best known results is Lagrange's four-square theorem, which tells you that every integer can be written as the sum of the squares of four integers. There is an example there with 15,663. Let me point out that these representations are certainly typically not unique. This problem, so that's particular example of a Diophantine problem. And this question was generalized by Waring, which is now about representation of integers as sums of Kate powers. So instead of representing integers by sums of squares, you want to represent them by sums of Kate powers, which is an active research area. For instance, just to give you one example, what is known is that every integer, when I say integer, I mean positive integer, is the sum of 9 cubes, and every sufficiently large one is a sum of 7 cubes, while it is believed that actually 4 cubes should already suffice. Just to illustrate that this is an area of research which is certainly far from completed. Now, after initial contributions by people like Euler and Hilbert, note that this is not the famous Euler, but his son. There was a new input brought into that field of the Diophantine equations, an input of analysis by British mathematicians Hardy and Littlewood, who developed a new method to study certain types of equations in integers. This method is called the Hardy-Littlewood circle method and was further developed by various mathematicians, in particular by another prominent mathematician, Russian mathematician, Vinogradov, mostly at the beginning of middle of previous century. So what Vinogradov brought forward is a system of equations which actually look very similar to the equations that appeared earlier related to the Schrödinger equation and the Korteweg-de Vries equation. It looks a little bit more complicated, but it has the same structure. So basically, what we are seeing here are, say, k equations. You see you have the exponent j, which goes from 1 up to k. So for each j, we're getting one equation in 2 s variables. And the number of integer solutions is subject to certain specific evaluations. The problem, like it is presented there, is purely algebraic, but alternatively, it can also be, the statement, the problem can also be described in a purely analytical way involving mean values of certain exponential sums, which brings us closer to actual wave interactions. So this system which you see here, which you saw on the previous slide, may look very special, but it turns out to be, in fact, a cornerstone of modern analytic number theory, and already the contributions of Vinogradov to that problem, which were substantial, led to really breakthroughs on the level of the Waring problem, the estimation of the Weil sums, and also on the Riemann zeta function and the distribution of prime numbers. Now, Vinogradov proposed what should be the optimal form of his result, sometimes called the main conjecture. This happened 80 years ago. There have been many contributors and contributions. Unfortunately, I cannot go into that, who did quite important work. And eventually, about a year ago, this conjecture, this Vinogradov problem, was completely resolved using the analytic formulation, so the one which relies on the exponential sum formulation, and amazingly, the same theory that allowed to make progress, for instance, in the theory of the Schrödinger equation, which is a harmonic analysis theory called decoupling, and tells us something new about wave packet interactions. So perhaps that was quite surprising that the problem of number theory got solved that way, while one was really expecting that it would require really number theoretic techniques, and apparently what did it were much more robust principles coming from harmonic analysis. And well, one could perhaps view that as a modest occurrence, a modest manifestation of a certain unity in mathematics, to which I will come back. Now, future challenges. Like I said, the resolution of this Vinogradov conjecture had some welcome, led to some significant further developments on the level of these number theoretic questions, like Waring problem I mentioned to you, also the estimation of Weil sums, but slightly less in problems related to the Riemann zeta function. You will immediately see what is the relation to Vinogradov's work and to the distribution of prime numbers. So since this is a talk for non-experts, let me just roughly say that when you're looking, prime numbers have always fascinated people for one or another reason. But anyway, when we're looking at prime numbers up to x, the number of them, the number of these prime numbers is roughly x over log x. And then one wants to have more precise forms of that, in some sense specifying what would be the error term. So the error term there, you see, predicted by the Riemann hypothesis, would be of the order of the square root of x. This would be, in some sense, an optimal form of the prime number theorem. What is the relation to the work of Vinogradov? Well, the strongest form known today towards a prime number theorem is this complicated formula which is written on the second line. That may not mean too much to you, but let me just point out that you have an error term there, which, although certainly very far from trivial, still comes a long way from proving something as strong as would be deduced from the Riemann hypothesis, which would involve a square root of x, basically. So this error term is relatively close to x. It's significantly smaller than x, or x over log x, but it is far larger than square root of x. So there is some kind of dictionary going back and forth between distribution of prime numbers and understanding zeros of an important object I will not describe in detail, which is the Riemann zeta function. So Vinogradov's work allowed to obtain, through the theory of Weil sums, new bounds in the related to the Riemann zeta function that then can be translated in new information about the zeros of the zeta function, which is far weaker than what you could derive from what you get through the Riemann hypothesis, but it's still strong enough to get some non-trivial statements, say, about prime numbers. So what can be hoped for is that through recent developments and also the multiplicative counterpart, which is the theory of Dirichlet series, which is kind of the multiplicative counterpart of Fourier series, there will be further progress. So let me, I don't know, I don't have much time anymore. Let me just take 1 minute to say something about, very briefly, about an issue called unity in mathematics. If you are a non-mathematician, it doesn't mean anything, presumably, or very little. But also, in the world of mathematics, this is something which is a very vague concept. As the word says it, unity means that there is a certain similarity and there are certain relations between different parts of mathematics and different techniques. So it is basically unity in mathematics is a perception of structural similarities occurring in different areas and problems. And often recognizing such analogies is the key to progress. But it can be misleading because, well, what people have tried is to push open problems by invoking principles of unity, and usually this kind of attempts, they fail, because this unity is more like something like a vague guideline than really a proven way to extrapolate. And unfortunately, realizing unity is often only apparent a posteriori, after the problem has been solved one or another way. So I think my time is up, and thank you very much.
Some time for questions.
No questions. Good.
It's all obvious. My question.
Any example of unity a posteriori you want to emphasize, and like past examples?
Well, yes. Thank you for asking me this question, because it gives me a little bit extra time to elaborate on that. So, as I mentioned, the Riemann hypothesis is by some considered as the most prominent problem in mathematics. Besides the problem itself, which is still open, it is a fact that this has been enormously influential in the development of modern mathematics. Like in other issues, like in turbulence, understanding Navier-Stokes has been quite important in pushing certain parts of mathematics. So although the original problem has not been solved, it had a great impact. For instance, returning to the Riemann hypothesis, it has developed a whole area through the work of Weil and then other people like Deligny and so on, the theory of function fields, where the Riemann hypothesis has actually been proven. So this is, of course, very encouraging, because you see that in a certain context, this question is resolved, and then one can try to learn the lessons from that and perhaps extrapolate whatever the methods that have been used there to come back to the original question. So people have tried to do that, but so far it has not been a success. And I mean, it's kind of clear there will be new ideas, and then later one will realize, well, after all, they are kind of similar to what was done in this function field area, although one can't go the other way around and just extrapolate that work. I guess that kind of gives a sense. Oh, it's quiet.
So my question is, you see the equality between the powers of the integers, right?
Yes.
So then I'm wondering, so since these integers don't have to be prime numbers, right?
Don't have to be what?
Prime numbers.
No, this is a problem about integers. There are no prime Wait,
So-
one can pose these problems in prime numbers, but originally they are posed in integers, yes.
So I'm wondering, so is it possible to be integers have their sum or their powers equals the other side? So I mean, have two different combinations of the powers of prime numbers have their equality.
Well, yeah, what I, of course, could not explain is how these questions of the type Waring was considering eventually connects with questions with, say, progress on distribution of prime numbers. And this is rather indirect. In some sense, these problems proposed by Waring, they may look kind of artificial. But what it turns out is that analytically, if one, at least with the known approaches, if one tries to study Weil sums or the Lindelöf, work on the Lindelöf problem on the zeta function or things like that, that these questions of understanding their Fontane equations in powers of integers, they come up naturally, and what turns out to be important is to be able to evaluate how many solutions they are. So the link with prime numbers requires you to go through an analytical process, which I didn't quite have the time to go into. And in fact, they go back to the work of Hardy and Littlewood and also Vinogradov.
Okay, thank you.
Try to answer the question.
So I think we should break for the half hour of a coffee break, but let's first thank both our speakers and congratulate them again on their awards.